thermochemistry is a subset of thermodynamics, and it's a part of thermodynamics. Thermochemistry is derived out of the first law, what we call the first law of thermodynamics. For any chemical reaction, two events must occur. For any this is the foundation, the statement of thermodynamics right there, right here. For any chemical reaction to occur, two events must occur. One, a change in energy, and two, a change in state of order. The change in energy and the concepts that revolve around that idea give rise to the first law of thermodynamics. And the change in state of order give rise to the second law of thermo. In the essence of a process taking place, everything must undergo these kinds of events. We all give up energy, but sometimes we build our energy levels by doing work. But everything that exists that's in this physical universe will change to something else over time. And in the process, it gives up what we call potential energy. Right now, you have a certain amount of potential energy, considerably more than I got. But the idea is your potential energy is eventually going to run down to where mine is. And that's a change of energy. Change in state of order, and you'll understand this when I show you. Everything rolls downhill, spontaneous. In the world of thermodynamics, reactions are defined as spontaneous, non-spontaneous, or at equilibrium. If we talk about a spontaneous reaction, it's like taking a ball, put it on the edge of an incline like that, and turning it loose. The ball will roll downhill in this reference frame without us doing any input beyond just turning the ball loose. So this is what we call spontaneous. And what happens is you go to a lower energy state and a more disordered condition. So the two events are taken into account there. And so smart people put a lot of math in it. Or if you have an incline and you place the ball right here, ask yourself, what's the probability of that ball rolling uphill on its own in this reference frame? There's none. I don't think, if it did, I think we'd all kind of get up and leave. So something has to be done in order to move the ball uphill. That requires work to produce the change in energy. And that's an endothermic process. We'll get to that. And we call that a non-spontaneous reaction. So in the world of thermodynamics, which deals with energy changes and changes in state of order, define chemical reactions in those contexts. First by changes in energy and then by changes of state of order. Everything's going to become more disordered. And you have to glue it all back together to make it more ordered. And you take into account, and the concepts take into account that. Okay, now why am I doing all this? Because I want to place thermochemistry in this idea of thermodynamics. Thermochemistry is a subset of thermodynamics, of the first law. It is based upon first law of thermodynamics. And is the study of energy changes in chemical and physical processes. So when we want to talk about changes, what do? We have a case one, our initial and a final issue. Well, that's what chemical reactions do. So for any chemical reaction, we have reactants going to products. And we say that before the reaction takes place, you have energy E of the reactants. That is the potential energy of all the reactants going to the potential energy of the product. So you start and finish, right? Final minus finish. So we all say, okay, what's the change in energy now? Well, that's easy enough. If we know what the number is that goes with the potential energy of the products, we subtract from that the potential energy of the reactants, and we have the change in energy. And that defines the change of energy. Well, in the world of thermodynamics, a change in energy can be shown. It can be shown that this differential depends on two issues within a chemical process. We call it a change of energy level and our heat and the capacity to do work. That is, a change in energy is equal to also heat of reaction, Q. How much heat is given off or absorbed by the process, and includes work. And the Q is called heat of reaction, and W is called work of the reaction. And therein is the two items we want to get into as far as this chapter goes. We want to define heat of reaction of a chemical reaction, and we want to define the work of the chemical reaction. Sometimes it's zero under certain circumstances, and you'll see that. So the equation for the first law is actually Q plus W, heat of reaction plus work of the reaction. Now, what we want to do now is talk about what is energy. Energy doesn't have a color, it doesn't have a flavor, but we know it's there as a result of some changes that take place in the course of the chemical reaction taking place. So we have to have an ability to study that. Energy, by definition, is the capacity to do work. That's what it is. That's what our physics friends tell us. When a reaction takes place, it's doing work, along with undergoing heat change. But work, by definition, is a force acting over a distance. And out of that, we can derive the units that are associated with heat of reaction and what have you. force from Newton's second law is mass times acceleration. And then we put back in there the distance, like that, and that worked. That. If we put in the SI units for this, mass is kilograms. SI unit for accelerated is meters over second squared, and distance is another meters. And so this gives us a complex unit, kilogram meter squared over second squared. And this is the foundation, or is redefined as the joule. So 1 joule is 1 kilogram meter squared per second squared. That's where it comes from. And I give you this to show you how it works back towards the definition of energy. Now, the other unit that we need to know is that of the calorie, a scientific calorie. And it's usually given by lowercase c in the course of everything. You'll see that c pop up in other contexts. No. The scientific calorie is simply 1 calorie, by definition, is the amount of heat required to raise the temperature of 1.000 gram of pure water 1 degree Celsius. The relationship between the calories and the joules is very important, because you will have problems that will require you to go back and forth between calories, joules, kilojoules, kilocalories, and on and on. Well, that conversion is 4.184 joules is equal to 1 scientific calorie. A nutritional calorie is the other side of the coin, of course, and that's 1,000 scientific calories. So we're not using that in that capacity. So our interest is strictly limited to the scientific calorie. This is a description of energy changes. Energy in itself is a byproduct of a change in structure and chemistry and physics of whatever's undergoing the chemical process. And when we describe energy changes, we describe them in terms of system and surroundings. So what you need to do to understand this is build a T-table. And we'll fill in the blanks on this. And so most of this is going to be terminology that you already know. In essence. On the left side, this is a system. And the other side is surroundings. And when we talk about the system, we're talking about the object of interest, the thing we're trying to study. Of course, that's the chemical reaction. And everything else is the surrounding side. So when we talk about energy changes, we're talking about heat flow. So when want to talk about the movement of energy or the change of energy, we have to define it in terms of heat flow. So what we're looking at is a flow of energy either from the system to the surroundings, or vice versa, from the surroundings to the system. And that's heat flow. Now, if energy is moving from the system to the surroundings, the system is losing energy. And we call that exothermic. Or exergonic, something. Exothermic. And that exothermic is with respect to the system losing energy. However, if energy is being absorbed by the system, it's gaining in energy, and we call that an endothermic process. And that's gaining energy. Now understand that when we use endothermic and exothermic, you must keep in mind that those terms relate to the system, not the surroundings, because if we consider the same endo-exo issues relative to the surroundings, we would find out that while it's exothermic to the system, it's endothermic to the surroundings. That is, the surroundings is gaining energy over here. And vice versa, it's exothermic to the surroundings. You're losing energy. If we're just looking relative to the surroundings. But that's not how the terms are used. The terms endo and exo, keep in mind, always refer to the system. That is the reaction. Is the reaction. Now, when I talk about, I'm not talking about reactants and products. I'm talking about both sides of the reaction. The entire process will either gain energy or lose energy or undergo isothermic, but let's just say they're all endo and exo today. I think so. Thank you. So anyway, that is very important that you understand that and how that those terms are applied in the course of talking about endo and exothermic reactions and generalizations. Now, associated with this is how do we measure changes in energy? The measure of changes in energy is measured in terms of temperature changes, because energy, changes in energy, is proportional to changes in heat flow, or the amount of heat in and out. That's your endo-exo, which is proportional to temperature. It is the temperature that you measure, temperature changes. Well, here's the thing about this temperature change. You don't measure temperature in the system. You can't. All the temperature measurements that you apply will be over here in the surroundings. All measurements occur in surroundings. And that'll give you a delta T, or a temperature change. And it's from that you make the decision whether or not the system is gaining or losing energy. Because if the temperature is going up on the surrounding side, it's got to be going down on the system side. If it's going down on the surrounding side, it's got to be going up on the system side. So it's opposite. But you have to make that interpretation. relative to the system, but you're measuring everything in the surrounding. And when you define the outcome of that, and you say, "Oh, that's exothermic," your interpretation is exclusively toward the system side of the reactor. So it's very important that you have this perspective in your mind as we go forward in there, because some of the problems that you're going to have to work is the system or the surroundings gaining the energy. And it's very important that you differentiate between those two. And some of you have heard of these before. One of them is specific heat. And it's given the symbol C. That is, the specific heat of water is 1.000 calories per gram degree Celsius. So when we talk about specific heat, this is the amount of heat, energy, needed to raise 1 gram of substance 1 degree Celsius. We have this on, and there's a handout. Right here. And these are characteristics of a given substance. When we talk about specific heat of a substance, now we've talked about the relationship, unit relationships, and because I needed some place to define something to define, and the calorie and the joules, and we use water as the reference standard. Well, what is a calorie? Well, it's the amount of energy necessary to raise temperature of 1 gram of water 1 degree Celsius. And then we related that to joules, 4.184. And so, but that number is the specific heat of water expressed in calories. It is 1 calorie per gram degree Celsius, but in joules, it's 4.184 joules per gram degree Celsius. So you look at the units in here, joules per gram degree Celsius. Over here, joules per, well, in calories per gram degree Celsius. They're different, but they are characteristic of the substance you are talking about. It's the amount of heat flow that will raise the temperature 1 degree Celsius. Or if you want to look at it backwards, it's the amount of heat loss that will decrease the temperature 1 degree. Same direction. Every substance has a specific heat. And here are some examples. Ice, steam, that gives you some numbers. And so that's how many joules each one of those has been measured and determined to be. They're constant. And they are determined experimentally, and on test day they'll be given in a problem and things. But these are specific to grams of substance. Grams of substance. Please hear that word, grams of substance. But we can talk about heat flow in terms of moles or a quantity of material. A second heat flow term is heat capacity. And that's a capital C. This is the amount, it's defined in the same way, except the quantity is different. The amount of heat needed, heat energy needed, to raise the temperature of a specified mass substance 1 degree Celsius. They're all based on 1 degree increases. That's each capacity. But the point is a specified mass. In other words, the mass hasn't been defined. So you could pick your own mass quantity, kilograms if you wanted to. Heat capacity in kilograms per degree Celsius and this kind of thing. Joule per kilogram degree Celsius. When we apply a specific mass, it becomes a more closer to a specific heat capacity. And one of them that is very important is molar heat capacity. You see the numbers, and that's C sub m. And that's the amount of energy needed to raise the temperature of 1 mole of substance 1 degree Celsius. So we have 3 terms that interchange themselves from time to time and may cause confusion if you don't know the definition. Primarily, the definitions will be defined and be related to solving problems, and we'll get to that. Specific heat deals with energy changes in grams. Molar heat capacity is energy change or heat flow in moles. Heat capacity is a generalization. You have to choose the mass factor. But heat capacity means how much energy does it take to raise the temperature of that quantity, 1 degree Celsius. Well, I've given you several examples in the handout to illustrate this. Here in calories per gram degree Celsius, and then here the joules per mole degree Celsius, and heat capacity, molar heat capacity, and others. And calories per mole degree Celsius. So those will come up as problems, and they'll mean more to you. But the issue is, how do we communicate energy changes and heat flow? And we do that in terms of specific heat, heat capacity, and molar heat capacity. Okay, now we get down to some specifics. Energy changes and chemical reactions. For any chemical process, reactants, go to products, and we have included in there an energy change. I'm going to put it plus energy change. Now, the way we define these in a more realistic context is we have what we call thermochemical equations. And they come in 2 symbolic forms. I'll use an equation to show you the idea. One way to write an exothermic reaction is as follows. Here's the ammonia synthesis. That would actually be tagged on the end down there. Now, what it means is that in this exothermic, you put a negative in front of the number. That indicates the exothermic, the reaction is exothermic, is losing energy. Okay, and that is proportional to the coefficients of the equation given. Now, a second way to write this equation, and both of them are used on the exam, so kind of get used to this, is if it's an exothermic reaction, the number can be incorporated in the body of the equation by putting it on the product side. And you don't put negative over there, you put plus whatever it is, because the endothermic energy will be on the reactive side, but it'll still be plus something of the reactants. I'll show you. So 3H2 plus N2 gas goes to 2NH3 gas plus 91.8 kilojoules. See, that's on the product side. And the fact that it is on the product side says that is an exothermic reaction. That's the terminology that you need. For an endothermic, reaction, we'll have a plus in the position of the energy number. For example, if I'm evaporating water from liquid to steam, gas phase, semicolon, delta H reaction is equal to 44 kilojoules. Just make it kilojoules. Right there. Now, if there's no symbol in front of the number, it's assumed to be positive. And as a positive number, that means it's endothermic. That the reaction, both sides, collectively are going to a higher energy level. You're starting at one potential energy, going to another potential. And so the differential is your heat of reaction. And that's this number right here. Incorporating the number into the equation puts the number on the reactant side like this. Both of these mean the same thing. And since we put it on the reactant side, it says, it's supposed to say, I'm an endothermic reaction. Whereas if it's on the product side like this is exo, and this is endo. Thermic type reaction. So I'm just giving you some notations that you're going to run into as you get into working problems and so forth and so on. So when we talk about energy change in a chemical reaction, we're talking about energy change of the internal energy kind or type. There are three kinds of energy in this world that we're working in. Potential energy, kinetic energy, and internal energy. Potential energy is stored energy. We will use that in a context. Kinetic energy and energy of motion, but that's mechanical motion. But the one that we're interested in is the internal energy. And we'll some delta EI, if you would, internal energy. By definition, this is the energy content due to the state of existence, chemistry and state of existence of the substance. So two things are really embodied in internal energy. The chemical structure and two, the state of existence. That is solid, liquid, or gas, or even aqueous. So when we talk about a change of energy in the problems we're about to work, you won't identify that in the context of the problem, but be advised or be aware that the products are not going to be like the reactants in chemistry or state of existence maybe. Yeah, sometimes it's all solids or gases or whatever, gas phase. But the structure, if you looked at the ammonia synthesis reaction, hydrogen plus nitrogen goes to ammonia, nobody looks alike. So that's what we're talking about. And each one of these has a certain energy content. And the structure content, energy content of the structural arrangements all go into a thing called internal energy. Well, we don't get into that specific. We just say, okay, we've got internal energy of reactants. And we have an internal energy of products. Like that. That's it. So the change of energy would be, if we know what the internal energy of the products are, and in the reactants, we take the difference, and we got a change in energy, change in internal energy. Yeah? That's it, long and short. So a change in EI is equal to internal energy of the products, whatever they are, minus reactants, internal energy. And I will show you how to get that. Reactants and products, take the differential. There's an equation for it. Very easy to use. In thermodynamics, however, that involves two changes. And I mentioned them earlier, maybe you remember, maybe you don't. Heat and work. So we can take in change internal energy is a heat for change in heat content plus work of the reaction. That's the process that we're going to attack right now. Change in internal energy is E products minus E reactants, which is now two terms. Heat content, or change in heat content, or the heat flow associated with the reaction, plus the work of the reaction. So this is the first law equation right here, Q plus W. Two things have to take place. And defining internal energy. Don't get that confused with the first law, second law events that we talked about initially. What we're talking about is coming up with a number that says, okay, what's the change in energy, internal energy of this reaction? Well, it's Q plus W. And I have to teach you how to get Q. I have to teach you how to get W. Once you get that, we add them together algebraically. Come up with a number and says, oh, okay, I'm finished. Q, being the heat of reaction, is also called enthalpy. And you'll see that many times. And it's given a symbology delta H of reaction with a little circle at the top. That little circle up there is what we refer to as standard thermodynamic conditions. And that's 25 degrees Celsius in 1 atmosphere. Now, the reason that's set up there is because all the tables in the back of the book that you're going to see here in a minute are all set up at 25 degrees in 1 atmosphere. And there's a way to calculate that enthalpy of reaction. And it's also heat of reaction. Work, W, is the work of the reaction. Now, to calculate that, I can go back into force times distance and substitute what we call a pressure substitution. And what you ultimately get is a term that you substitute for W is P delta V. Actually, it's Vm. And so this is pressure times the change in molar volume. So in a reaction, say 3H2 plus N2 goes to 2NH3, you have 4 molar volumes on the left. This only applies to gases. And you have 2 molar volumes on the product side, right there. And so your change in molar volumes, which is what we're talking about here, is 2 minus 4, or a decrease, minus 2 Vm. So overall, that's what it's saying. So you just add up the gases on the reactant side, product side, take the difference, and that's your change in molar volume. Well, we'll get to that. That's called a compression reaction because you're decreasing the volumes. Going down. You came out with a positive over here, that's an expansion reactant. And those are important, and I'll show you why in a minute. So for determining internal energy, 2 things are going to be required. You got to calculate enthalpy of the reaction, usually it's tagged on the reaction anyway, and the work of the reaction. And the units will be kilojoules per mole or kilojoules. All right, let's see how this all comes together now. Okay, so the object here is to determine the change in internal energy of a reaction. We'll use the ammonia because I've used it so much. Determine, based on that data, change in internal energy. Change in internal energy is Q plus W, which is delta H of the reaction, standard conditions, plus P delta V. You need 2 things. You need heat of reaction. That's calculation number 1, if you need to calculate. And then work of reaction. Once you get those, you algebraically add them together and you get the final answer. In this case, the heat of reaction will be 91.8. It's given right there in the equation now. In some, you'll have to calculate it, and we haven't got there yet. So our delta H of reaction for this problem is a minus 91.8 kilojoules. You have to put the negative back in since it's an exothermic. But what is the work? This is P delta V. Well, I worked this out in the past, and it turns out to be 2.5 delta Vm. Like that. Now, I'm going to put little brackets around that because you're going to have to apply something that is kind of skewed. And once you get used to it and you see what I'm doing, you have to apply signage to that. Now, and I'll get to it. Sometimes the first law is Q minus W in engineering text primarily. And I'll show you why they are still the same. Q plus W. I use Q plus W because that's what's in EBI. That's what they use. It can get confusing, but hopefully I can clarify. So what we're going to do is look at this equation and get us a delta V. It doesn't matter whether it's plus or minus. Just get the change in volume. It's 2, the absolute change in volume. And then times 2.5. Then you'll have to assign a sign. I'll show you how to do that. Okay? I'm going to tell you what it is first. This is 4 molar volumes going to 2 molar volumes, and it decreases, and that's a compression reaction. If it's a compression reaction, assign plus to 2.5 delta V. So this we'll put a plus on, and then algebraically add it back to a minus 91. Don't try to fight it right now. If it's an expansion reaction, assign a negative to whatever you get out, 2.5 delta V. Trust me at this point. So for the reaction we're working with right now, delta EI equals delta H of the reaction, algebraically plus 2.5 delta V. Now bracket that, but you've got to put a signage in there. For this reaction, since it's an exothermic reaction, we got a minus 91.5 kilojoules over here. Then we're going to add to that, and I'll leave a little space in here, 2.5 times 2. Now, if it's a compression reaction, which it is, because you are going from 4 molar volumes to 2 molar volumes, it's going to be an endothermic work factor. So you put a plus in there. That's what I'm trying to tell you. And yeah, the change in volume is 2 molar volume, 4 to 2. Absolute. Don't worry about signage right there. So just whatever the change in volume is, absolute, times 2.5, you make an assignment based on compression expansion. So the delta EI for the reaction now is minus 91.5 plus 5.0, and it will come out in kilojoules. Already been determined in another life. But anyway, it comes out in kilojoules. I never can remember. This reads the change in internal energy is 86.5 kilojoules exothermic. Change in internal energy. Just a number. But it takes into account both the work function and the heat of reaction. 2 things that are involved in a chemical reaction. They need 2 things. What are they? You need delta H of the reaction. Well, in this case, it's given to be plus 44 kilojoules. It's endothermic because it doesn't have a negative in front of it. And we need the work, which is 2.5 delta V. And then we have to assign a signage, negative or positive. Well, what's the delta V in here? Well, molar volumes of any liquids and solids is 0. Molar volumes only apply to gases, guys. So this is 1 Vm over here. So you're expanding from 0 to 1. So your Vm right here is 2.5 times 1, or 2.5, and this comes out in kilojoules. I should keep putting that on there. Now, since it's an expansion, assign, what did I say? A negative to the work, which gives us work to equal a minus 2.5 kilojoules. So I put that in because of the expansion. Now here's the rationale. Well, let me finish the problem. Delta EI is now equal to 44 kilojoules plus a minus 2.5 kilojoules, because that's what you're putting in. This is exothermic work. The other one was endothermic work, compression. And so kilojoules. That's your net change in internal energy for the evaporation of water, because it has to do work on the surroundings. Now here's the rationale on it. If you think of the reaction in terms of mixture of particles together, then the reactant side may be at this volume level, and you've got a number of particles, whatever they are, doesn't matter. Just a bunch of particles in there at volume 1. And if you compress, you're going to a smaller volume with the same number of particles. So you're going to that, but now they're all squeezing together. Squeeze the balloon to volume 2, where volume 2 is less than volume 1. Squeezing the balloon, you'll find if you do that with an inflated balloon, it'll push back on your hand. Why? Because they're gaining energy. So going from this V1 to a smaller volume with a fixed mass in it, the particles are going to gain energy. And therefore, endothermic work occurs, or a plus. So that's why on a compression reaction, you have to put a plus once you determine it. That's the nitrogen, hydrogen to ammonia. You went to a smaller volume. So it's like squeezing the balloon. You have to put a plus in there because the particles are pushing back on your hands. On the other hand, if you start at a small volume with those and go to a larger volume with the same number of particles, they're further apart. I think of them as relaxing. It's like removing the walls and letting them move out away from one another. So from V1 to V2, particles are losing energy. And the expansion, I should put that up here. Reaction, which gives you more particles in gas phase than you started with. The particles spread apart, lose energy, and so this is exothermic work. And you assign a negative sign. When you do the 2.5 delta V, and then you put your sign in. But the differential, increasing, decreasing, just tells you if it's compressing or expanding. Now, as long as you've got the delta H and the changes in volume, you can calculate any delta E for any reaction, EI. What we're doing is determining internal energy of chemical process. And fundamentally, it boils down to change in internal energy, which is product minus reactants. And this boils down to heat of reaction and work. Two separate calculations have to be dealt with. And these are shown in this expression, heat of reaction and P delta V. P delta V is the work of the reaction. And I've condensed that down into a simpler equation here that's delta H plus 2.5 delta V. And in working with the equation, at this point in your understanding, the delta H is attached to the equation and is separate from the work function. So all you got to do is look at the equation and see what's tagged on the end of it, or which side of the equation is on. For the 2.5 delta V, you have to look at the gas phase components and make an assignment of sign. You either have endothermic work or exothermic work going on. And with that in mind, if you define endothermic and exothermic relative to the expansion of the reactants to products or compression from reactants to products. If it's an expansion, you assign a negative sign in here and then algebraically add it back to the energy number, or the heat of reaction number. If it's a compression, you assign a plus and add it back to the enthalpy number, like that. So this is kind of a thumbnail. And keep in mind also that the sign of the delta H is already determined by another mechanism altogether. These are two separate calculations, and you'll see how that evolves as we get deeper into the subject. So what have we accomplished up to now? Calculating the internal energy of a chemical reaction. That's where you are right now. I've written it as open versus closed reaction systems. In thermodynamics, when you talk about the first law of thermo and you pick a chemical reaction, it's either an open reaction or a closed system reaction. Say it again. An open system reaction or a closed system reaction. Well, how do you tell? From the equation, if delta V, molar volumes, does not equal 0 when you do your molar volume change, then it's an open system. If it's an open system, you have to take into account the work function. That's what we've done so far, this 2.5 delta V. I'm going to put an M on that, right there. However, if delta Vm does equal 0, actually equals 0, then we call it a closed system. And that's unique in that what happens is delta E internal energy, which is equal to delta H plus P delta V, this becomes 0. And the result of this is that delta E internal energy is nothing more than the heat of reaction. And you lose the work function. There are 3 scenarios that define closed systems. So keep in mind that when we talk about closed systems, the energy for a closed system, this term goes out to 0 and everything just reduces down just to internal energy equals heat of reaction, like that. Well, there are 3 scenarios. First one, if the sum of the change in molar volumes of the reactants, R, is equal to the sum of the change in molar volumes of the products, you have a closed system. That's gas phase reactant, sum of gas phase products, take the difference and you wind up at 0. Bomb calorimeter system. In this, the reaction is conducted in a fixed chamber that doesn't expand or compress. So we say it's got a delta V of 0. I'll show you one in a minute. Or what we call a solution phase reaction. Where you take, say, an acid and a base, for example, you can have more than that. An acid and base, when they interact, have a tendency to give off energy or absorb energy, depending on the reaction. However, while they change in temperature, we can measure it, the water or the solution itself doesn't expand or compress. We assume that water or the solvent is incompressible or doesn't expand, regardless of how much it heats or cools. For the first case, where we have the sum of molar volumes of the reactants equal to the sum molar volumes of the products, and this is simple enough to understand, you have hydrogen gas plus, say, chlorine gas that goes to 2HCl gas, hydrogen chloride gas. Over here you have 2 molar volumes. Over here you have 2 molar volumes. And so the change in molar volumes in these 2 minus 2 is 0. And so the only thing that's involved in that reaction is whatever the delta H of reaction is. And so that is equal to internal energy. Okay. Those are pretty easy to identify. You just look at them, and you add up the products and the reactants, take the difference. If it's 0, then the only thing you have to consider is the heat of reaction. It's usually a delta H number hanging on the end of the reaction. That's a bomb calorimeter. Now, the way this thing is constructed is a device, or an apparatus, that has a reaction chamber in the middle here. And that reaction chamber is surrounded by a water jacket inside another chamber, like that. And of course, you have a thermometer submerged into the water jacket. And so you place a substance on a stage that's inside the reaction chamber and flood this with oxygen. And then you send a charge through to ignite the reaction, combustion reaction. All combustion reactions are exothermic. So energy is going to be given off, and that's going to move into the surroundings, the water, and the thermometer is going to detect that. And you'll have an increase in temperature for whatever your substance you are looking at. Because all the bomb calorimeters reactions are oxidation reactions or reactions with oxygen. Okay, and then from that you determine the molar heat of reaction and all the other stuff. A unique equation goes with that. For a bomb calorimeter, the amount of energy, heat flow in the given calorimeter is given by C sub V delta T. And C sub V is what we call the calorimeter constant. And it's assigned by the manufacturer. As a constant, so to speak. So the only thing you really have to be concerned about as far as calculating the amount of heat flow is the delta T number. Well, that's easy enough. You just look at the thermometer before and after. You start the reaction. Now, there's one little twist to this. All right. You're given a mass of graphite, pencil lead, okay, 0.562 grams. And you start out in the water jacket has 25 degrees, and then you run your reaction, and it winds up at 25.89 degrees. The calorimeter, assigned calorimeter constant is 20.7 kilojoules per degree Celsius. Now, with these, you can get a delta T equal 25.89 minus 25 equal, well, degrees C, 0.89 degrees C is your delta T. And with the C sub V and then the delta T, you can get the heat flow for that reaction in the quantity as C sub V delta T to 20.7. This is a given. It has to be given. 20.7 kilojoules per degree C, and your observation is 0.89 degrees C. Very simple problem in this context, and the test problem would be the same. And so Celsius drops out. 18.423 kilojoules. Okay. Now, the trick here is that is for a very small amount, 0.562. If the question comes to you, says what is the molar heat of reaction, that's for this small amount. You have to convert this to moles and then divide into that number to normalize it to wind up with kilojoules per mole. And that's on the exam. So, this up here, look at that. So, the molar QM for the molar heat of reaction, molar heat capacity of the graphite now is 18.423 kilojoules, and that's for 0.562 grams. So we divide that by 12, the 0.562 by 12, and we get it in moles. (12 grams per mole), and we get the molar heat of reaction. That's all it is to that. The trick is be sure you recognize that when the problem comes to you, it'll be for a itty-bitty bit, small amount. And you have to convert that to moles and then divide into whatever you get for C sub V delta T. And it's no more complicated than that for a bomb calorimeter problem. The next one takes some time. Solution phase reactions. To understand this, first thing is that it's a closed system because the liquids do not expand or compress. There's no gases involved in here. This is like reacting an acid solution with a base solution, pouring them together, and you come out with a heat of reaction. Okay, just in measuring the temperature change. If you have an acid solution with a base solution, you get increase in temperature of the solution, or final solution, let me say that. And the solution is part of the surroundings. Acid, base, mix. Okay, and you put a thermometer in there, this thermometer is going to go up. Is the reaction endothermic or exothermic? It's exothermic. Because the solution is surroundings endothermic. Remember, the system is opposite whatever the surroundings are. As the temperature goes up, the solvent, when you pour these two together, the solvent is the surroundings. It's not the reaction. So the reaction is sending energy out into the surroundings, into the water, into the beaker, into the air, into the universe. And so that's what you're measuring. You're measuring the change in temperature of the surroundings. An increase in temperature, yeah, okay, that's an exothermic to, endothermic to the solvent. But exothermic, the heat had to come from somewhere. It came from the reaction. So that's why you interpret the outcome of your experiment in terms of the reaction, the system. Now, Now, the heating curve of water shows a transition from ice below zero, below melting point, through the melting, through the warming of the liquid, through evaporation, and up to some assigned temperature. So this is a phase change diagram as well as what they call a heating curve for water. So our problem that I'm trying to get you to work and learn how to work is this: determine the total amount of energy of heat energy required to convert 10 grams of ice at a minus 10 degrees Celsius to steam at 110 degrees Celsius. The constants you will need are specific heat of ice, water, and steam. We're going to work in calories, and you can convert it to joules and multiply it by 4.184 if you wish. Water, specific heat is 1, as you remember from start out when we defined the joule, the calorie. That's 1.00 calorie per gram degree C, and steam is 0.48 calorie per gram degree C. So you'll need those three specific heats. You'll need transition constants, delta H, what we call delta H of fusion, which is the heat needed to melt a specific mass of ice, and that turns out to be 80 calories per gram. Let's see if I can clean that up a little. And then you have a transition for evaporation called heat of vaporization. And that is equal to 540 calories per gram of water that you're evaporating. You'll need those constants to work this problem. Okay. 5 regions in here, and this axis, vertical axis, temperature and degrees Celsius. Horizontally is heat in, out. You can go either way on this curve, cool or heating. Okay. So we're going to start right here and say this point right here is minus 10 degrees C. And this one is 0 C. Here we're at 100. And this one will be, right here, be 110. Right there. Notice how we've got slope lines and flat lines. The slope lines are pure condensed phases. What that means is this is the heating of the solid, heating of a liquid, heating of the steam of the gas, whatever you're using. The horizontal lines do not show temperature changes. Those are transitions. When two phases are in contact, temperature change is 0. Now, that may sound strange in that context, but when you have ice water, it cools to a certain point and does not keep cooling or warming until all the ice is melted. So when you boil something, boil water, the water will boil at a constant temperature until all the water is converted to steam. So anytime you have two phases in contact, in this case solid liquid phase in melting and liquid gas phase in evaporation or vaporization, each one of these has a certain amount of heat. See, this is heat quantity going horizontally. If we're looking at a sloped type line, here, here, and the gas phase right there. If you're making a calculation in solid, liquid, or gas, any heating area, the amount of heat, Q, is mass times specific heat times the change in temperature experienced, MC delta T. So you'll have an MC delta T for warming the solid, an MC delta T for warming the liquid, and an MC delta T for warming the gas to whatever limit you set. In the regions that are transition regions, that is here and here, those show no temperature change, so then the equation is not going to have any temperature. But what it has is Q for your transition is M delta H of whatever that transition constant is. So while you're melting, you would have delta H of fusion, that's what it is, delta H of F. When you calculate the evaporation, you'll have a delta HV number there, they're constant. And you just substitute the mass, like we're working with 10 grams. 10 grams times whatever the heat of fusion is. And so that's the number that goes with that. And 540 calories per gram times 10 grams, 5,400 calories to evaporate that part. So you have a way to calculate each of the lines in here. You calculate them individually. And then you add up everything at the end, and that tells you the total temperature. Total heat flow, sorry. So we'll start here warming from minus 10 to 0. So Q, we'll call that Q1, is MC delta T. We start with 10 grams. Specific heat of the ice is 0.50 calories per gram degree C. That's a given. And the delta T is 10 degrees C. As we went from minus 10 to 10. Minus 10 to 0. So the change in temperature is 10 degrees. Grams will drop out, Celsius will drop out, and you have 50 calories. Then you go to number 2. That will be your melting. Now, since there's no temperature change, you want to select an M delta H transition or M delta H fusion. So that's M dot delta H effusion of water, and we're still melting 10 grams, and it's 80 calories per gram, and so that's 800 calories. Then you go to number 3, the liquid, warming the liquid, region 3, and since that's a temperature change region, MC delta T, we have 10 grams of liquid water now, 1 calorie per gram degree C, and it's going up 100 degrees C. And so that's 1,000 calories. And you keep going until you run out of regions to check or calculate. Q4 now is an evaporation region, no temperature change, so you want an M delta H expression. So that's an M dot delta H vaporization, and that's 10 grams Delta HV for water is 540 calories per gram given, and that's 5,400 calories. And then the final region is warming the steam from 100 up to the 110 is an MC delta T because you have a temperature change involved. And it's 10 grams and 0.48 calories per gram degree C, and you're going up 10 degrees C, and that's 48 calories. So we want to add those together. I never can remember this number, but anyway, times as I've done this. So I just went down the list, and I got 7298 calories. The last threw them off. Work ourselves into a grave them on. Here's what, yeah. Now some of the constants in here are not exactly like I give. I've used constants because they're easier. And they use joules as your transition constants and specific heats and so forth. Well, that's fine. I just converted them to calories because they're easier numbers to work with while I'm making a presentation like that. But if you look at these, the essence of the problems that you're working is it in a temperature change region? Is the problem deal with a temperature change or not? You hear me? That's the bottom line on these problems. It's a matter of, do you use MC delta T or do you use M delta H only? Or a combination. I'll show you that when we get to calorimetry. There's another worksheet. But changing phase means that you heat and then melt or heat and evaporate and whatever. So you have to determine whether or not you're evaporating, freezing, warming, or what. And once you determine that, then you'll know which equation to use. And there are only two, MC delta T or M delta H. All right, let's see how it works out. Now, I'm going to use constants I don't like, okay? In this first example, I got how many joules are required to heat 250 grams of liquid water from 0 to 100 degrees. So how many joules okay, like I say, you have fragments of the heating curve. Okay, so when you look at this problem, you kind of have to make a little diagram of where you're starting. So we're starting at 0 degrees and going up to 100 degrees. So your delta T in here is 100 degrees C. That immediately tells you you're working with a temperature change problem, and that the heat, as heat in out, is calculated using MC delta T. Now, I don't know what they give specific heat, but this is a warming of water. I'm going to use calories. If C equals 1 calorie per gram degree C, and you've got your mass is equal to 250 grams, what's the problem? Plug and chug now, right? I mean, it's a no-brainer after you determine whether it's a temperature change problem or not. That's the long and the short of this. So you simply have 250 grams times 80 calories per gram times 100 degrees C. Oh, wait a minute. I'm not doing that. 1 gallon per gram degree C. Okay, I'm using the confusion. Okay. Grams drop out, Celsius drops out. And so we have 250 and another couple of zeros in calories. And 25,000 calories. I know you want it in joules? All right, kilojoules, okay. Times 4.184 joules per calorie. See what that gives us. Hey, it's just a matter of what you need it in or what they're asking for. That's just nothing but a conversion. And so the 104,600. And of course, divide by 1,000, that's 104.6 kilojoules. 105 kilojoules. Like that. So you see, once you determine temperature change or not, you know which equation to use, and based on the data given, is more of a conversion problem at the end of it than it is anything else. Given mass is 100 grams of water. Okay, A Q for melting is M times delta H fusion, and in this case 100 grams times 80 calories per gram. Wait, I won't do it. And so that's 8,000 calories times 4.184 joules per calorie. Calories drop out, whatever that comes out. $33,472 joules. I don't know what they wanted here. They want kilojoules? Yeah. So 33.5 kilojoules, 3 sig figs, assuming that 100 grams is. We melted. Let's see. B choice. Q vaporization is also an M dot delta H equation, but here we use vaporization right here. So that's 100 grams and 540 per gram. That's 54,000 calories times 4.184 joules per calorie. That drops out. What does that come to?
So that one, by the way, you started out with 150 grams, not 100.
They want 150? Oh, okay, okay. That's easy to fix. $81,000. Okay. Thank you, sir. 4.184. So that's 338,904 joules divided by 1,000, 339 kilojoules. It's very straightforward kind of idea. I didn't have this for here. Now, there are some that will throw in your toes. I'm going to show you some of those right now. 3, 4, 5, and should be able to 4 and 5 is be able to do the same thing.
Are those constants going to be on a cheat sheet?
Absolutely. Okay. Or either embedded in the problem. Okay. Either way. Now, I do have some problems where you give it everything else and calculate the specific heat. or a constant involved in the process. So you'll give it all other superfluous data, but you still use the same formula and solve for the unknown. Well, you got to go with what's going on in the problem also. You're going through several phase changes. How many joules are required to heat 200 grams of water from 25 degrees C to 125 degrees C? So you're starting at 25 degrees C and you're going up to 100. You got to start there. And so you got to evaporate all your water, and then you go up to, say, 125 degrees C. So that's your warming after the evaporation thing. So you have a liquid, and then you have liquid gas, and then you have gas warming. So you have three regions. Is that what you did? Yeah. Yeah. So here and here, Q equals MC delta T, and this one is Q equals M delta H of vaporization. So you have two of those and one of those. Add them together and you voila. I'll set it up. That makes sense, guys? You just have, when you see something like number 3, it's 25 to 100, you have to keep in the back of your mind you're still working off of the phase changes and the heating curve. You have to take them into account up to the limits that are defined in the problem. Good question. Anybody else? All right, let's work one that's got some meat to it. This thing. Now, it's always good to draw you a picture of what's going on. And then you kind of get a relative idea of how things are changing. So in this, number 3, you have given a 30 gram sample of water at 280 Kelvin is mixed with 50 grams of water at 330 Kelvin. And so we need these, actually you need to convert these to Celsius. Because MC delta T is going to be given, I don't know, maybe they give you the constants in there. I don't see the constants at all. But anyway, I'll give you constants in degrees Celsius. What have you? So wait a minute, 280 minus 273. All right, so we're starting at 7 degrees Celsius here. And 330 minus 273, 57 degrees C. So you're going to pour these two together and come out with a final temperature, T final. Is this a temperature change problem or not? It's all temperature change problem. Because what you're doing is taking a cold water and some warm water, mixing them together, and you're going to wind up somewhere in the middle of those two. You're going to have a temperature change of the cold water, increasing or whatever it is, and then you're going to have a cooling effect for the temperature change of the warmer water. And they're going to wind up mixed together. Okay, how do you know how to set this up? Well, when working with mixtures, it's called the method of mixtures. Now, some of you may have done these kind of problems before from in another life, but the one I use is Q, the energy changes are the sum of all the energy changes, Q values, always equals 0. Law of conservation of energy. So you look at the problem and you think sum of all the energy changes. Well, I've got an energy change here in the first one, an energy change in the second. That's a temperature change between the two. They're going to wind up in the middle somewhere. And both of them will have an MC delta T. So what I have is an MC delta T for the water cooling plus an MC delta T for the water warming. Like that. Now, and all that equals 0. I've got to put that on the end. So what I will work with is exclusively that portion down there. And it works on every one of these kind of problems. Now, if you had melting ice, you'd put an M delta H in there. So this is an MC delta T for the cooling. That's starting up the warm water cooling down to whatever the final temperature is, plus an MC delta T for warming. All of that equals 0. Every problem you have a mixture of issues, ice or something hot, cold. You're either cooling it or you're changing phase. It's still an MC delta T or M delta H problem, but you have to decide on how many heat changes you're taking place, and then make a sum of all those and set them all equal to 0. Now the advantage of this is you can always work temperature T final minus T initial. You don't have to set heat loss equal heat gain and try to figure out which way to switch the temperature. It takes care of itself in the problem that you're solving. It's the simplest way. So in this, what do we have in the who's undergoing cooling? Well, we've got 50 grams of water undergoing cooling, 1 calorie per gram degree Celsius. You want to work in 4.184 joules per gram degree Celsius. That's fine. And your temperature change, well, is T final minus initial temperature is 57 degrees. Okay, I'm going to bracket that. That's my MC delta T for the cooling the water. Plus the mass of warming, so that's this 30 grams of water, 1 calorie per gram degree C. That's all given the constant. And again, it's T final minus initial. We start at 7 degrees. All that's going to equal 0. And you combine terms and solve for the unknown. Now, one of the things that I tell students in problems like this, trust me, it's set up correctly. If you understand what I'm doing here, drop all the units out. It simplifies the algebra. 50 times 1 times TF minus 57 plus 30 times 1 times TF minus 7. Doesn't that look a whole lot less toxic than all the units piled in there? It's going to come out in degrees C. I don't care how old you get. It's always going to come out in degrees C. And so now I start simplifying. I have 50 onto the TF minus 50 times 57 plus, I'm going to keep the brackets in there so we don't get lost in the units, in signage. So this is 30 TF minus 30 times 7. Bracket that off, and it says 0. So simplify your algebra, kind of keeping books in the thing. Maybe I'm old school. That's happens. 57 times 50, 2850. So I have 50 TF minus 2850 plus 30 TF, 210. And all that's 0. I'm still using the sum of all these little changes. So all I did is identify it. Well, how many different changes are going on in here? Now all I got to do is solve for TF. So that's 80 TF. And so that's, let's see, minus, I put 210. 3060. All that's equal to 0. And so 80 TF equals 3060. And your final temperature is 3060 over 80. And trust me, is in degrees C. And will come out between the extremes that you're mixing together. 38.3. It's just 38 degrees. Now you started at 7 and 57 and wound up in the middle. The issue is this, understanding that solves all of those kind of mixture problems. It's just, you have to, the hardest part is saying, okay, what's going on in the problem? Well, I got some melting and I got some warming and I got some cooling, and odd and end. So each one you have to apply. Okay, so you'll have problems like this. Okay, somewhere in your mixture of questions you have. You got temperature changes going on everywhere. Look at number 1. Okay, so calculate the specific heat of a metal. All right, 174 joules is required, so I'm going to say Q is equal to 174 joules required to raise 50 grams mass, 50 grams from 25 to 50 degrees. T1 is 25 degrees C, T final is 50 degrees C, delta T is 25 degrees C. Is that a temperature change problem? All day long. What equation do you use? MC delta T equals Q. So Q equals MC delta T. They're asking for C, and so that's Q, whatever it is, M delta T. So that's the kind of problems you will see also. And so C in this case is 174 joules, 50 grams, and a delta T of 25 degrees Celsius. Grams, I need to put the units in. And whatever that comes out to be, 30.033, 0.1392 joules per gram degree C. So that's a standard units for specific heat, joules per gram degree C or calories per gram degree C. Specific. Remember I said in the terminology you'll have to be aware of specific heat terminology. Well, that's related to gram heating or molar heat capacity or molar heat, molar heat capacity, and that would be heat per mole degree Celsius. Those kind of things. Okay, number 5 down there is kind of just a heat, serving the heat needed to raise the temperature. Okay, what's it got? Calculate the amount of heat needed to absorb. That must be absorbed to raise the temperature of 4.75 grams of tin. Mass is equal to 4.75 grams. 10. T1 equals 25 degrees C. T2 to 26.8 degrees C. And I give you the specific heat of 10, 0.21 joules per gram degree C. And so if it's a temperature change problem, no brainer now. That's a Q equals MC delta T. We got 4.75 grams, 0.21 joules per gram degree C, and 26.8 minus 25 degrees C. C's drop out, grams drop out, and you're left with joules right there. That's 1.8, so that's 4.75, 0.1, 1.8. That's 1.8, that don't work. Thermochemistry is really a study of the first law of thermodynamics. And we find that the first law is dealing with the change in internal energy of the system which is energy of the products, internal minus internal energy of the, product minus the reactant. And that boils down to Q plus W. So in thermodynamics, first law deals with calculating or determining what is the change in internal energy of the system, which involves chemistry, physics of the system, as well as the state of existing solid, liquid, gas. And this evolves to delta H plus P delta V. Well, the internal energy in this form has two, well, I should put it in the middle. Let me put that in the middle. Has two kinds of problems that you got to be dealing with. One of them is called an open system problem, and the other one is called a closed. The open system problem, delta V does not equal 0, and in a closed system, delta V molar, does equal 0. So that turns these into applied type equations. And so what do we do? Then change in internal energy now is delta H of the reaction plus 2.5 delta V if you have an open system and you have an equation and you're given the delta H number. All you got to look at the change in volumes. If it's an expansion, you put a negative on the work. If it's a compression, you put a plus on the work. However, if it's a closed system and delta V equals 0, that simplifies the equation to delta E internal energy just simply to the heat of reaction. And P delta V goes to 0. Well, this embodies those three areas that we talked about. So if the molar volumes are equal on reactant product side, you've got a closed system. If you're working with a bomb calorimeter, you've got a closed system. And if you're working with solution phase reactions, which was the last several problems, you've got a closed system. And those are MC delta T problems and M delta H problems. And that's it. So over here, you have Q equals the MC delta T or Q equals M delta H problems, given, and then we work just the scouring. And then over here, the only thing I have to give you now is what other ways can I use to calculate delta H? And therein is Hess's law, is what we call it. And those are nasty. If you haven't seen it, we'll work on these in the morning, but if you thumb through it, you'll see something that looks like this. Those are adding equations. And we'll start with that in the morning after our quiz. In these kind of problems, if you look at your worksheet, you'll have a target reaction, and then you're supposed to add these two equations together to get that target. And the algebraic sum of the energy numbers, after you flip them around and multiple and divide by and this, that, and other, gives you the net heat of the equation. This kind of problem is when you have a reaction that you can't actually run in a bomb calorimeter. It always gives you mixtures. If you run a reaction like hydrogen and oxygen, you might get water and hydrogen peroxide out of it, or CO2, or you mix sulfur and oxygen, you get SO2 and SO3, and you just need sulfur and oxygen to give you SO3. Well, what's the reaction there? This is how you do that. You'll have there are standard equations published, and then you pick those equations, add them together to get the target reaction, and you can get the heat of reaction out of that. It takes getting used to, and I'll work several out of this. And then there's Hess's law. Hess's law is very straightforward, but you have to understand what I mean by standard heats of formation and how to apply those to Hess's law. Okay,